Welcome to the course Introduction to Algorithm. My name is Sourav Mukhopadhyay. I am a faculty member at IIT Kharagpur. I am lecturing this course. So today is the third lecture of this course, Divide and Conquer. So in this lecture we will discuss divide and conquer technique, which is a algorithmic technique to tackle certain type of problem. So and we will see some of the known algorithms, known problems can be solved using these techniques. So in just to recap, in lecture 2 what we have done, we have discussed three methods of solving the recurrences, and that recurrences is coming from some algorithm on time complexity. So once we solve the recurrence on time complexity, we will come to know the time complexity, asymptotic time complexity. So we discussed three methods there: substitution method, recursion tree method, and master method. So in this lecture we will discuss divide and conquer technique. This is an algorithmic technique, and then we will discuss some of the problems which can be solved using this technique, and we will discuss their time complexity. So let us start with the divide and conquer technique in detail. So divide and conquer technique has three steps. First step is divide. So we have given a problem, we need to solve it. We have given a problem of size m. For example, we have seen the merge sort. Merge sort comes under this divide and conquer approach. So we have given an array of size n, we need to sort it. So what we did there, we divide the array into two sub array of equal size n by 2 n by 2, and then we recursively sort that two sub array by same merge sort call, and then once we have a sorted sub array, two sorted sub array, we call the merge to get the sorted array. So that was the example of divide and conquer technique. In general, divide and conquer technique has three steps. First step is divide. We have a problem of size n, we divide that problem into sub problems of lesser size. So it could be two sub problems, it could be three, it could be many, depending on the problem. So we divide the problem into sub problems. So that is the divide step. Sub problem size should be lesser, and then once we have those sub problems, we conquer those sub problems by solving them recursively. So we get the solution of these sub problems by solving them recursively. So this is a recursive call of the same function of the same algorithm. We solve them recursively, and once we have a solution of those sub problems, it could be 2, it could be 3, it could be more. Once we have the solution of these sub problems, then we combine the solutions to get the solution of the whole problem or problem instant. So that is this technique is called divide and conquer technique. So basically three steps: divide step, then we have to conquer those sub problems by recursively solving them, and then once we have a solution of the sub problems, we combine them to get the solution of the whole problem. So as we know, the merge sort comes under this. So in the merge sort, if you recall what we have merge sort we discussed in lecture number 1. So in merge sort we have a array of size n and need to be sorted. So what we did there, so this is a problem in size n. So we divide this array into two sub array. This is n by 2, this is n by 2, and this is also n by 2. We divide this array into two sub array. Now this is the divide step. We just divide this. We just take a index over here n by 2. That is the merge sort divide step. It is very trivial. Just we need to find the index, and then we call the merge sort on this sub array recursively. We call the merge sort on this sub array. So that is the conquer step. We conquer these sub problems by solving these two recursively. So that is the conquer step. And once we have a solution of these two, once these two sub-array are sorted. So, that means once we have a solution of these sub problems after solving them recursively after this conquer step, then we have to combine to get the solution of the whole array, whole problem. So, that is done by the merge subroutine. If you recall, we had a merge subroutine which is input is two sub-array, sorted sub-array, and then we call merge to get a sorted, get a whole array to be a whole array which is sorted. So, that is an example of divide and conquer technique. So, now it is if we get the time complexity of the merge sort, this was the recurrence we have received. So, every divide and conquer technique or approach will result this type of recurrence. Not only merge sort, every divide, we will see some more divide and conquer problems. Then we will get this type of recurrence, because we have a problem of size n in the merge sort and that problem is divided into. So, this was the merge sort recurrence. We have this to sort this, we need t, if Tn is the time to sort n elements. So, array size n, then T of n by 2 is the time to sort this subarray and T of n by 2 is the time to sort this subarray. So, the total is 2 Tn by 2 and this is the cost for merging and combining together. So, this is the cost for combining means merging and divide. Divide here is trivial, constant time, but combine is this is a linear time algorithm we have discussed in lecture 1. We had a linear time algorithm for doing this merge subroutine. So, this is the, so in general, so every divide and conquer approach will give this type of recurrence, where this is nothing but number of sub problems. In merge sort it is 2 and this is nothing but the size of the sub problems. Here it is equal size and this is nothing but the time for divide, which is for merge sort it is theta of 1, and time for combining. So, together. So, this time is for both divide and combining. So, we get this type of recurrence for merge sort and this has some significance. Now, we may have some cases we may have some different size array also, different size sub problems. In that case, we won't get this type of form, we may get T of n by 2 plus T of n by 4 plus theta n. So, that depends on the problem and the algorithm which we need to solve this problem. Okay. So, next we will talk about some example, more example other than merge sort, which can be solved using this technique, divide and conquer technique. So, first example is very known example, known problem, which is called binary search problem. So, before that, let us recap the master method for solving the recurrence, because we are going to use this for getting the time complexity of our problems. And so, master method recurrence is of this form, Tn is equal to a Tn by b plus Fn. So, this is a recurrence coming from a problem which can be think of a divide and conquer technique. Like we have a problem of size n, we are dividing the problem into a many sub problems of size n by b, and this is the cost for combining those sub problems. So, this is the cost for dividing and combining both. Okay. Now, there are 3 cases. So, details was discussed in lecture 2. There are 3 cases of master method. That cases are coming by comparing 2 terms, Fn and n to the power log a base b, this term, this Fn and n to the power log a base b, whichever is the more. So, this first case is Fn is polynomically slower than n to the power log a base b, that is the way we can denote that, and in that case the solution is, so n to the power a log a base b is the dominating term, is polynomically faster term. So, the solution is the time complexity will be Tn is equal to big theta of n to the power log a base b. And now, in the case 2, their growth is similar, Fn and n to the power log a base b, their growth is similar. So, that is the way, or they can differ by a log factor. This is log in base 2 or a power of log factor. In that case, solution is Tn is equal to big theta of n to the power log a base b log, this is base 2 n to the power k plus 1. And if k is equal to 0, most of the cases we will see that like for March sort, k is equal to 0, March sort comes under, recurrence comes under this, for this case. Okay. And the third case is Fn is polynomically faster. So, that is the way we can show that Fn is polynomically faster than n to the power log a base b, and we have an extra condition which is called regularity condition. So, this, if these two satisfy, then Fn is the first dominating cost. So, Tn is the big theta of Fn. So, these details we have discussed in lecture 2. So, now we will talk about we will solve the March sort recurrence. So, for March sort we have Tn is equal to 2 Tn by 2 plus Cn. So, A is 2, B is also 2. So, n to the power log a base b is n, and Fn is also n. So, it is comes under case 2 of this master method with k is equal to 0. So, it is basically solution is n log n. So, this we have already discussed in lecture number 2. So, now we will go for some more example which can be more problems which can be solved using the this divide and conquer technique. So, first problem we will discuss now is binary search problem. So, what is the binary search problem? Binary search problem input is an sorted array. We have a sorted array of say n numbers, and we have a element, we have a candidate, we have a element to be searched in this array. So, this is a searching problem. We have given a array of say n element which is sorted. So, this is the input, this is starting from say 1 to n. So, this is a array, and this array is sorted. This array is sorted. We have n numbers, sorted numbers given in the array, and we have a element x, or we can say key or something like that. We have element x. We need to search this element in this sorted array, whether this is there or not. So, this search is important because if this is a database problem and if we have stored some of the records, then we may need to search the record. So, we can search a roll number, whether that roll number student is in the database or not. Anyway, search is having many applications. Okay, so this problem is called binary search problem. So, you have two input over here, a sorted array and a number and a element key to be searched. So, this problem, so we how to solve this problem? We can search linearly, we can search one by one, whether this is matching with this is matching with this. So, that will cost us how much? Linear time, because that is we just keep on checking. So, this is basically a for loop. So, for say I is equal to 1 to n, 1 to n, 1 to n. What we do? We just check whether x equal to, whether ai is equal to x or not, x equal to ai or not. So, we just searching linearly, and if it is matching we return, otherwise we continue until I exhaust. So, this will cost us linear time because this is a loop in n, and here checking this is a constant time because we are dealing with asymptotic time complexity. So, we do not really bother how much exact time our computer is taking for doing this job, that means how much second. So, that time we are just taking as a constant c. So, that is theta of 1. So, total time is theta of n. But here we are not using the information that the array is sorted. So, we have extra information array is sorted. So, how we can make use of that? So, that algorithm we will discuss. We can use the divide and conquer technique for doing that. So, we just check the middle element, middle of the array. Okay. So, we just, this is the same middle of the array. So, we check the middle of the array element. So, if the that is a of n by 2 or a of n by 2 plus 1 lower ceiling upper ceiling. So, that is okay. So, we check the middle of the element if it is matching with x or not. So, if it is matching, then good, we are returning that okay, x is there in the array. Otherwise, if this element, if x is less than middle, there are three possibilities: equality, less than, greater than. If x is less than middle element, suppose this is 7 and we are looking for say x equal to 2. So, definitely 2 won't be here because this is a sorted array. So, 2 won't be here because every element over here is greater than 7. So, 2 has to be here. So, what we do? We call this binary search again on this subarray. So, this is kind of divide and conquer. So, it has 3 steps: divide step, we check the middle element whether it is matching or not. If it is matching, okay, otherwise if it is, if the middle element, if the key value, if the value we are searching is less than that, then we will recursively search that in this subarray, or if it is greater than, suppose we are looking for 9, then 9 has to be, if it is at all, it has to be in this subarray. So, that part we will just do recursively by either searching here or searching here. So, that is the only one recursive call. So, combine step is nothing, that is the very trivial, we are not doing anything in the combine step. So, this is the divide and conquer technique we have discussed for doing this. Let us take an example, quick example for, suppose we have given this input 3, 5, 7, 8, 9, 12, 15. So, this is a given input which is a sorted array, and we have a key value say 9 to be searched here, whether this 9 is there in this sorted array. So, what we do? We just check the middle element. So, middle element is 8. So, we check 8 and 9. If it is matching, then we can just stop things, otherwise. So, 9 is greater than 8. So, we will just that is the divide step, the checking middle element. 9 is greater than 8. So, we will go for the right subarray to search it, because it will not be in the left subarray, because 8 is the value up to here. So, if 9 has to be there, it has to be in the right subarray. So, then we check 9 on this subarray. So, if 9 is there, then on this subarray again we will call recursively on the same binary search. We check the middle element of this, middle element is 12. Now, we compare 12 and 9. So, 9 is less than 12. So, we just do that again the recursive call. 9 is so recursive call, that is the subarray. We come here, that is the again the recursive call will occur. So, that will match now, and we say 9 is there. So, that is the thing. So, what is the recurrence over here? So, recurrence is we have only one subarray sub problems, because we are only searching in right subarray or left subarray, not both, and this is the size of the subarray n by 2, because we are just dividing into, dividing means we are checking in the middle, either we are going left or right, and this is the work we are doing for dividing and combining. Combine is nothing, we do not need to combine anything, but dividing part we are checking the middle element, that checking is taking some constant time. So, that is theta of 1. So, this is the time complexity. Now, how to solve it? Again we use master method. Here A is 1, B is 2, we calculate n to the power log A base B, which is n to the power 0, which is 1, and theta n is also Fn is also 1, I mean C say, this is the case 2 with k is equal to 0. So, the solution is Tn is equal to big theta of n to the power log A base B, which is 1 log n, that is k is equal to 0. So, k plus 1 log n. So, this is the solution for this is the solution for the binary search algorithm. Okay, so next problem we will be talking about the powering a number. So we have a number a. So the problem is to find a to the power n. So a and n are both the input of this algorithm of this problem. So for example, if we need to find 2 to the power 100. Okay, so 2 to the power 100. So that is the problem. So 2 and 100 both are the input of this. So now the question is how to do that. So the naive approach is we can keep on multiply a with n. So this is basically a into n times or n minus 1 times. So that is a into so that is the naive way we can do this. So we can have a dot 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 n minus order of n times. So this is the way we can do this. So this is a for loop. If we have to code this is just a for loop. We can just keep on multiply a with the value. The value is initialized by 1 and then we can keep on multiply. So the what is the time complexity for that? Time complexity will be order of n, because we have a order of we have a n minus 1 multiplication is there, and each multiplication will take const theta 1 time. So naive approach is order of n. So now we want to do something better than this, whether we can apply some divide and conquer technique for doing this. So because to find 2 to the power 100, we can just 2 to the power 100 can be written as say 2 to the power 50 into 2 to the power 50, same value. So that is the idea. Again 2 to the power 50 can be written as 2 to the power 25 into 2 to the power 25. So that is the divide and conquer idea. So what is the formula? Formula is this: if n is even, suppose you have to for example this one, n is even. So if n is even, a to the power n is nothing but a to the power n by 2 into a to the power n by 2, if n is even. That means 2 to the power 100 is nothing but 2 to the power 50 into 2 to the power 50. So now if we recursively call this, so there is only one call, because if we now we divide the problem into sub problems. This is our initially problem size was n. So we have to find the power of n. So power of a comma n. Now n is reduced to n by 2. Now we need to find a to the power n by 2. Once we get the solution of this, once we get the value of a to the power n by 2, we will multiply with itself to get the solution of the whole problem, a to the power n. And if n is even, if n is odd, that means if we have to find say 2 to the power 101 or say 2 to the power 51, 51 is odd. So this is nothing but we can say 2 to the power 25 into 2 to the power 25 plus 2. So that is 25 is n minus 1 by 2, n minus 1 by 2, and then we have so that is also a divide step, because we reduce the problem into lesser size, and size is of order of n by 2, because this is just a n by 2 minus half. So that is just a half, means lower ceiling or upper ceiling. So that is also order of n by 2. Only thing we need to use this formula if n is odd. So this is the divide and conquer formula for doing this. So we divide the problem. Our problem was of in size n. We divide the problem into sub problems. Now we need to calculate power of n by 2, power of a comma n by 2, and that again we can further. So that will be taken care by the conquer step. So in the conquer step we recursively find this. So only one. Once we get we don't need to call again this, because once we get the solution of this, we can multiply with itself to get the solution of the whole problem. Once we get the solution of this, if n is even odd, then we multiply with itself and then we multiply one more a, and that will be 3 multiplication, 2 multiplication, here we have 1 multiplication. So, combined step is this multiplication, and that is also order of 1, because multiplication is taking constant time we are assuming. So, what is the recurrence? We have the recurrence like this. We divide the problem into 1 sub problems of size n by 2, and this is the cost for divide and combining. So, this recurrence is same as the binary search recurrence, and the solution is big theta of log n. So, this is a log n time we can do this powering a number. Okay. So, this is better than the n. Okay. So, next problem we will discuss is Fibonacci number. If we these problems are known problems, but we want to see this problem in terms of this divide and conquer techniques. So, this is called Fibonacci number. So, we know the Fibonacci number is like this. So, first Fibonacci number or 0th Fibonacci number is 0, and next Fibonacci number is 1, and after that we have this records this formula. So, basically we have this. This is first Fibonacci number, 0th Fibonacci number, this is F1, this is now next one is this plus this. So, that means F2 is F1 plus F0, so which is 2, and then once we have this, then to get this plus this is 2, and 2 plus 1 is 3, and 3 plus 2 is 5, and 5 plus 3 is 8, 8 plus 5 is 13, and 13 plus 8 is 21, like this. So, this is the Fibonacci number. Now, we want to find Fn for a given n. So, this is the way we are going. Suppose our problem is to find, say, what is the F2020, say F2020. So, in general we want to find what is the Fn, n will be a input. So, you want to know the nth Fibonacci number. Given a n, what is Fn? See, if for the lower value we can easily get from here, but for large n, say F2020 or F1000, 1 lakh, what is the value? So, that is the problem. That is the problem is called finding the Fibonacci number. So, how to do that? How to solve that problem? So, we can, the bottom up method is we can keep on calculating. We can get like this way. We get the first Fibonacci number, then second, then third, fourth. Only thing we need to, every time we need to store the last 2 Fibonacci numbers. So, that storage is constant, because just a 2 number need to be stored. So, this way F0 we calculate, then F1, F0 F1 is known, 0 and 1, then F2 we can add these two, F3 like this. So, we can continue up to Fn. So, every time we will store the last 2 number, and this how much will be the cost, because we are going up to n. So, the cost will be runtime is order of n, because n addition we are doing basically, and this is what is called bottom up approach, but we want to do something better than n. So, that we want to see whether we can use the divide and conquer technique for doing that. So, for that we know the formula on Fibonacci number, that Fn is phi to the power n divided by root over of 5. This phi is basically, we know what is called golden ratio. Phi is 1 plus root 5 by 2. So, this relation can be proved by the solving the recurrence relations. So, this is a formula we know. Fn is nth Fibonacci number can be written as phi to the power n by root 5. And this is Fibonacci number must be an integer. So, this need to be, and these are not, this is not integer, this is a real number, 1 plus root 5 by 2, this is a real number, and this is also real number, root 5. So, they are not integer at all. So, now, but Fibonacci number is an integer Fn for any n. So, we have to rounded this value to the nearest integer. So, this is a squaring a number, but here the squaring a real number, and problem with that. So, when we do this multiplying, then we have to think of rounding off how many points. So, that's why this method is not a realistic method, because it will take more time for those fixing those arithmetic, like how much the point rounding off. So, this will take some more time for doing that. So, this is not just easy 2 to the power 100. So, it is not the powering of an integer, it is powering of a real number, floating point. So, floating point arithmetic is will take some more time for doing that. So, it is not just log n time for doing this. So, this is not a realistic way to do that, but we do have a approach for doing this in order of log n time. So, that we will discuss. So, for that let us take this theorem. This theorem is telling f of n plus 1, this is n plus 1th Fibonacci number, f n, this is f n, this is f of n minus 1, this is a matrix, 2 by 2 matrix. So, this matrix can be shown to be 1 1 1 0 to the power n. This needs a proof. So, this proof we will do by again by induction, mathematical induction. So, if we have this formula, if we have this theorem, then we can have an algorithm, because if we have to find f n, so we can, if we can calculate this matrix to the power n. So, if we can calculate this like a to the power n, so A is this matrix, a to the power n. So, A is this 2 by 2 matrix, A is just this, A is 2 by 2 matrix. So, yeah, A is this matrix. So, now a to the power n, if we can calculate, if we can get the result of a to the power n, that will be again 2 by 2 matrix, and in this 2 by 2 matrix, so this will be something like some value a b c d, a b c d, because this is a 2 by 2 matrix and we are keep on multiplying. So, eventually the result will be a 2 by 2 matrix. So, once we have a 2 by 2 matrix, so this is nothing but this. So, these two BC will be same, and these two BC, this value will give us Fn basically. So, basically to find a to the Fn, we need to calculate this a to the power n, this matrix powering a matrix, but here this matrix is a 2 by 2 matrix, it is not a bigger matrix. So, that can be that can use the like similar to powering that number, because a to the power n can be written as, so a to the power n can be written as, this is the recursive formula, recursive this is the divide and conquer formula, a to the power n by 2 into a to the power n by 2, if n is even, otherwise we have that formula a to the power n minus 1 by 2 into same thing a to the power n minus 1 by 2 into a, if n is odd. So, that means this is a divide and conquer formula. So, to solve this we can just recursively call this solution, and that will be reduced on this size n by 2. So, this is a divide and conquer technique, and it is just the same formula, T n is equal to, so what will be the recurrence? Recurrence will be T n is equal to the time complexity. How many sub problems? We have one sub problems, and what is the size? Size is half, T n by 2 plus what is the cost for divide and combine? Divide and combine is just a constant, so it is C some theta of 1. So, that is that will give us log n. So, that is we have seen, but we need to prove this formula. So, if this formula is true, then we can use this formula, we can get this a to the power n to get the value of f n. For example, if we have to find say f 2020, how to get f 2020? If we have to find f 2020, n is 2020 say. Okay. To get this, if we can just get this matrix 1 1 1 0 to the power, this is a matrix to the power 2020. So, this is basically a 2 by 2 matrix and power is also will be 2 by 2. So, this will be some value A, B, C, D, and this is nothing but BC will be same, because this is nothing but f, this two value will be f 2020. These two value, I mean these two value are same BC and they are nothing but f 2020. So, that is the idea. So, to get the Fn, we need to get the value of this. So, now the question is whether this theorem is true or not. So, this we will prove by the help of the mathematical induction. Okay, so now we will prove this theorem by the help of mathematical induction. So, the theorem is telling f of n plus 1, Fn, f of n minus 1, this matrix 2 by 2 matrix is nothing but 1 1 1 0 2 by 2 matrix to the power of n. So, how to prove this? We prove this by mathematical induction. So, this is the base case. So, base case is telling this result, this is a properties is n. So, we want this result, the base case is the result is true for n is equal to 1. So, if you put n is equal to 1, this is f0, f1, f2, f1. So, that is nothing but f0 is 0, f1 is 1 and f2 is 1. So, this is basically true for n is equal to 1. So, base case is done. So, now we need to assume that this is true for that induction hypothesis. We need to assume that result is true for n is equal to k, and then we need to show that result is true for n is equal to k plus 1, or we assume the result is true for n is equal to n, and then we are going to show the result is true for here we have tried with n minus 1, that means we assume that result is true for n is k is equal to n minus 1 or up to n. So, we assume the result is true for up to n, and then we are going to prove that the result is true for k is equal to n. So, that is the thing we are doing. Okay. So, now if we multiply this with this matrix with this 1 1 1 0. So, what will be this matrix? So, this into this. So, f of, just let us calculate that. So, this is f of n plus f of n minus 1. So, this is basically f of the first element f of n and then plus f of n minus 1, and that is nothing but f of n plus 1, that is the recursive definition of the Fibonacci numbers. So, that is why it is f of n minus 1, and now this into this. So, this into this means f of n. So, this is f of n. So, this row and this column is f of n. So, this is f of n. Now, the second, this position. So, this position is this plus this. So, this is f of n minus 1 plus f of n minus 2. So, this is basically we have f of n minus 1 over here, this is minus 1 and f of n minus 2, and that is nothing but fn, because fn is the sum of the previous two Fibonacci number. So, previous two Fibonacci number is fn minus 1 and fn minus 2. So, that is nothing but fn. So, this is our fn. So, fn is so this is fn. Now, this term is f of n minus this row and this column. So, that will give us f of n minus 1. So, this is okay. So, this matrix into this is coming out to be this matrix f of n plus 1 fn f of n minus 1. Now, we assume that the result is true for up to n minus 1. That means the result is true for up to n minus 1. So, that means this f of n. So, if you consider this matrix, now under the induction hypothesis, this matrix will be we use the formula, the assumption, induction hypothesis, the assumption is the result is true for up to n minus 1. So, that is it is 1 1 1 0 to the power n minus 1. Now, with this it will give us 1 1 1 0 to the power n. So, the result is true for n. So, we assume the result is true for n minus 1, then we can by this step induction step we prove that the result is true for n also, and we already proved the base case. So, base case was the result is, we have already proved the result is true for n is equal to 1. So, by this inductive step we can show that then the result is true for n is equal to 2, and once we have the result is true for n is equal to 2, then the result is true for n is equal to 3. So, this way the result is true for all n. So, this is the inductive proof of this theorem, and this theorem is very useful for finding the nth Fibonacci number for a given n. So, basically we need to just calculate this matrix to the power n, but this matrix is just a 2 by 2 matrix. So, it is very much similar to powering a number. So, in the 2 by 2 matrix, so the multiplication when we talk about, so a to the power n by 2, if n is even, so a to the power n is basically a to the power n by 2 into a to the power n by 2. Okay, so this is the divide step. If n is even, if n is odd, this is n minus 1 by 2 into n. Now, this is a matrix of size 2 by 2, and this is a matrix of size 2 by 2. So, now when we multiply 2 by 2 matrix, then how many addition, how many multiplication will be required. So, that is constant. So, a, b, c, d, x, y, z, w, then we have constant number of multiplication and constant number of addition. So, that is why the combined cost, because this is the combined cost, when we solve this, when we get the result this recursively, so that is the concord step, and after concord step we need to combine. So, when we have this, we have to multiply by itself. So, when you multiply by itself, that is the combined step. So, combined step also, this is eventually this is a 2 by 2 matrix, say a, b, c, d, these are some integer, and then we have again a, b, c, d, the same matrix here we are using a, b, c, d. So, we have to multiply these two matrix. So, this is basically this row, this column a square plus b c will be the first element, and this row, this column. So, eventually we have few addition, few multiplication of the these numbers, integer or real number. So, integer especially. So, this will be the constant time, theta of 1 time. So, that is why it is the divide and conquer step, it is theta 1. That is the reason we get the recurrence Tn is equal to Tn by 2, because we have only one sub problems, because once we get this value we will just use it to multiply by itself and then theta of 1, theta of 1, and that is the recurrence for powering a number, which is the solution is big theta of log n, big theta of log n base 2. So, this is the time complexity for finding the this matrix power, and eventually it will give us the nth Fibonacci number, because once we get the matrix, this matrix is again a 2 by 2 matrix. So, from that we can get the Fn by taking this corresponding value of the result. Okay. So, this is how to get the nth Fibonacci number. So, next example we will be talking about the matrix multiplication, and we will see how this matrix multiplication can be solved using divide and conquer technique. Okay. So, in the matrix multiplication, just to recap, we have a matrix A, which is basically A11, A12, this is the first row, this is second row, this is the nth row, and we have another matrix B, this is first row, this is second row, this is nth row. Here we are taking those two matrix size as same, but multiplication could be on general matrix. So, for matrix multiplication we can have two matrix size, A size could be m by P, and then the B could be, B matrix could be P by N, P by N. Then also we can do the matrix multiplication. But here for the simplicity we are taking the order of the matrix to be same. So, they are of n by n cross n matrix, both of them are n cross n matrix. So, they are of same order, here we are assuming. So, we have two n cross n matrix, and we need to multiply that, multiply and get the C matrix, which is a multiplication of these two matrix. So, C is also n cross n matrix. When you multiply n cross n, then you will get n cross n matrix. And C is again Cij. The Cij is basically, this is the say ith row of, we have a ith row of A, which is basically ai1, ai2, ain, this is a ith row, and we have say jth column. So, if you recall the definition of matrix multiplication, it is basically inert product between these two. So, it is basically summation of aik into bkj, where k is varying from 1 to n. So, this is the inert, this is the formula for matrix multiplication we know. And we have, maybe you have coded it in C language or any language in your data structure course. So, that is the code we are going to discuss now. This is very standard code you have seen. So, basically we need to find this Cij. So, this Cij for all I and j. So, so this is C11, C12. So, Cij is the ijth element of this C matrix. Okay. So, we need to find theCij's for all I and j. So, that we will do in a for loop. So, I is varying from 1 to n, j is varying from 1 to n. So, for all I and j, this is our Cij. So, Cij is basically summation of, if you recall the formula, Cij is nothing but Cij is basically summation of aik, that is the ith inert product between ith row of A and jth column of B. So, that is the k is varying from 1 to n. So, that is our Cij. So, that we are writing in this formula. So, we initialize Ci by 0 because we have to add this. Then for this we are k running, we each time we are calculating this aik ij are fixed. So a I k, so k is 1, we get a value, and then b k j, I j are fixed once we enter into this loop, and then we add with this c I j, pb as c I j, and it will give us a c I j. So this, after this sum we get, after this loop we get c I j, and this we run for all I and j from 1 to n. So this is the very standard formula for finding, very standard code of finding the matrix multiplication. Now what is the time complexity for this code? So the time complexity is basically whatever we are doing here. We have a, how many loops we have? We have 3. We have a, this is a for loop over here of size n, this is another for loop over here of size n. Now whatever doing over here is constant theta of 1. This is just a assignment, we are doing some constant time over here, and this is another loop of size n, but whatever here we are doing is another constant c1, so theta of 1. So we have basically 3 for loop, each of size n, and everything inside is theta of 1. So that will give us order of n cube algorithm. So this standard matrix multiplication algorithm time complexity is order of n cube. So now we want to see whether we can do it something better than order of n cube or not. Especially we want to see whether we can use some technique like we know divide and conquer technique for this problem, for the matrix multiplication problem. So let us try that. So for that we have to divide the problem into sub problems. So for that what we do, we write this matrix into sub matrices. So this is A matrix, capital A. So A matrix we are writing into sub matrices. This is A is a sub matrix of size n by 2 cross n by 2. So B is also sub matrix of size n by 2 cross n by 2. So suppose this is our A matrix. What we are doing? We are dividing into 4 parts. Okay. So this matrix is small a, this matrix is small b, just a represent notation small d. This is our A matrix. So provided this is possible, provided we can assume that this order, because n by 2 may not be an integer, so then we have to take the lower ceiling or upper ceiling. But if you assume that n is a power of 2, then everything is fine over here. But anyway, we will discuss this for asymptotic time complexity, so for large n. So in that sense it doesn't really matter. So this A is a matrix which is n by 2 cross n by 2, B is another matrix which is n by 2 cross n by 2, C is also another matrix which is n by 2 cross n by 2, D is another matrix which is n by 2 cross n by 2. Similarly, B matrix we are writing this. So B matrix is E, F, G, H. So this is our A matrix, and similarly we denote the B matrix as this. This is our B matrix, similar way. Okay. Now this is our C matrix. We do the similar way. So these are the sub matrices. So now what is the formula? So this sub matrix will multiply with this plus this and this. So R is basically, the sub matrix R is basically AE plus BG, and S is basically, S is this one. So this means this into this. So AF plus BH. So AF plus BH. So T is nothing but CD with B multiply with this. So CE plus DG. CE plus this is this into CE plus DG. This will be, this is a mistake. See, this should be CE plus DG. So this will be G over here. It's not H. So this is a G. Okay. So now U will be this into this. So this into this. So CF. So U is basically CF plus DH. So this is fine. So this is a recursive formula. So this is a divide and conquer. We divide the problem. So now Here is also matrix multiplication, A into E. So, this is A into E. So, this is a matrix multiplication, this is also B into G. So, this is also, so these are all sub matrices. So, we reduce the, earlier the matrix size was n by n. Now, this matrix multiplication here we are doing on size n by 2 cross n by 2, both this A and E, all of this. So, we reduce the problem into sub problems. So, earlier it was of order n cross n matrix, and this is order n by 2 cross n by 2. So, this all the matrix sizes n by 2 cross n by 2. Earlier it was. So, that is the divide step. Now, we solve this, we conquer this by solving them recursively. So, that is the conquered step. So, we have how many matrix multiplication? 1, 2, 3, 4, 5, 6, 7, 8. So, we have 8 matrix multiplication we need to conquer, and then after that we have to add them. So, that will come under combined step. So, after the recursive call, after solving this, after get the result, this will be n by 2 cross n by 2, this will be n by 2 cross n by 2. So, then we have 4 addition, and all of this size n by 2 cross n by 2. So, what is the cost for addition? It is basically we have to add corresponding elements. So, it is of order of n square, because size is n square by 4, if we treat this as a vector. So, order of n square. So, we have a recurrence like this. So, we have 8 sub problems, because 8 multiplication we need to do, and then size of the sub problems we just reduce to half, because earlier the matrix size was n by 2 cross n by 2, and now it is n by earlier n by n cross n matrix, now it is n by 2 cross n by 2, and this is the cost for dividing and adding also, the adding the sub matrices. So, that is the cost. Now, what is the solution for this? Again, if we use the master method, this is A, this is B. So, n to the power log A base B is n cube, but this is n square. So, it is of case 1. So, case 1 means time complexity will be big theta of, because this is the dominating term, big theta of n cube, which is not as good as the standard method. The standard method is also was giving n cube. So, then the idea of Stresson's came. So, Stresson's idea is to reduce the multiplication by 8 to 7. So, it was having 8 multiplication. So, now question is how we can reduce this multiplication by 7. So, that is the idea of Stresson. So, idea is to reduce the multiplication by 8 to 7. So, for that what Stresson did, he calculated some of the intermediate values. So, P1, P2, P3. So, these are basically A and this sum matrices. This is some A and F, G are the sum matrices from B. So, if we can calculate this, then this, if we add it up, if we take some of the value, R is P5 plus P4 minus P2 plus P6. So, this formula we have to prove this, you can just verify this. So, maybe here we can just verify one. So, R. So, R is, we are claiming P5 plus P4 minus P2 plus P6. So, what is P5? P5 is A plus D into E plus H. If we break it up, AE plus H, then D plus this way. And what is P4? P4 is DG minus DE. So, if we do that calculation, eventually we will get AE plus BG, and that is nothing but R. If you remember, our R was AE plus BG. R was AE plus BG. So, similarly, this is the R. So, similarly, you can check all the others, other one. All the other we can check by just putting these values. So, these intermediate values if we can get, then by adding these values we can get this matrix C. So, these are the sum matrix for C. So, that is the idea. So, we are how many multiplication we are doing? We are doing 7 multiplication, because 7 intermediate value, and with the cost of more addition, the subtraction is also addition, minus or plus. So, with the cost of more addition, we are reducing the multiplication. So, that is the idea of station. So, that way we can say how many multiplication we are having 7 multiplication, but we are doing some more addition, but that does not matter, because that will be come under order of n square. So, whether 4 multiplication 4 addition or 18 addition does not matter, the subtraction is also kind of addition. So, this will be this will cost order of n square. So, that will come under divide step or combined step. So, this is the divide step, because we have to calculate this in order to call this recursively. So, in the divide and combine step together we are doing 18 addition or subtraction. So, that will be costing us order of n square. So, that is the recurrence. So, this we partition, this is the divide and conquer technique, we partition this, we divide this into sub matrices, and then we conquer by solving this 7 sub matrices, 7 multiplication, and then we combine. So, now this is the recurrence. So, 7 multiplication instead of 8 multiplication. So, that will give us the nice result. So, if you solve this using master method, it will be reducing n to the power log 7. So, n to the power 2.81, which is better than order of n cube, which is better than n cube, because this is in power. Okay. So, now conclude this lecture. We have discussed the divide and conquer technique in general, and then we discussed the merge sort as a divide and conquer technique, binary search problem, powering number, Fibonacci number, matrix multiplication, the stations idea. So, in the next lecture we will be discussing another divide and conquer technique on sorting, like quick sort. So, that we will discuss in the next lecture. Thank you.